C'est parti.
Okay, so good morning, everyone, and thank you for the invitation to present a work that we recently published with colleagues from Bordeaux INP about the life cycle assessment of basically computers in the context of higher education. So first, I'm Adrien Vincent, and I'm an associate professor at NSERB Matmeca, so one of the schools at Bordeaux INP. So first, what this presentation will be about. So basically, as I said, we are going to have a look at the content of an article that we recently published about a year to a year ago with some of my colleagues. So in the International Journal of Life Cycle Assessment. And in a nutshell, the study was about performing the life cycle assessment, a comparison of life cycle assessments between a scenario with desktop computers and a scenario with single board computers and servers. Yeah. So just to be clear, if I say LCS, that's for life cycle assessment, but I guess that everybody in the room knows that. So, and I would like to acknowledge those 4 students who actually de-risked the whole project. I mean, the whole work by a semester project without even knowing that it would be used in the first place for that kind of work. Yeah, so my presentation will have a quite direct outline following most of the different steps of a life cycle assessment. So we will define the goal, we will perform the inventory, and I will provide a few insights on how we did manage to perform such an inventory, because I think that what you are really interested about based on what Pierre told me. And then we will have a look at the results of those LCAs and try to interpret them. And I will finish with some discussion and concluding remarks regarding what could be the next step. So regarding the context of the study, so it starts in a village where we still call chocolatine what's actually pain chocolat. So it's near Bordeaux, and it's in the context of a graduate school in electronics, computer science, and other topics related to the digital electronics, basically. So that's NSERB Matmeca. And in that school, we have about 1,200 students, not new students, but students over 3 years. And as most of our teachings are related to the digital domain, we use quite a lot of computers. So basically, we have about 600 computers that we use during lab works and that are also freely available for the students. And when we perform basically the assessment of the carbon footprint of the school, that was one of the main contributor to our carbon footprint impact. And those computers are used for quite simple engineering tasks, except maybe a few specialized simulation on top of that. So that's where our idea for the functional unit come from. Basically, we wanted to evaluate the environmental impact of the use of those 600 computers over their 5-year-long lifetime. So in the context of our engineering school. And the original idea was actually to build or to design a lab work to introduce life cycle assessment to students in the context of new teachings that were being introduced in the syllabus. So the tools that we used and the assessment method, just to be clear, so basically for all the background information, we use the IncoInvent database, which is kind of one of the main generic databases that are available here. For teaching purposes, it's quite affordable, okay, and we already had actually one license in Bordeaux INP. And we use the database in the version 3.5. We'll see the impact of that choice, but that was what we had at that moment when we launched the study. We performed the calculation using OpenLCA, which has the advantage of having a nice graphical user interface, which is easier to introduce the students to. And regarding the assessment method, we opted for recipe 2016, and we perform midpoint analysis, meaning that we stop, at all those 17 or 18 impact categories. And just here, I mean, we will see a lot of abbreviations in some of those graphs, so just know that they are on that slide, and I will provide the slide later if you need. Okay, and we will have a look more in details to some of those categories, as those are the one for which it's the easiest to provide interpretation of the results that we will have. So, as I said, the two main scenarios that we wanted to consider were first the actual current setup that we have in our engineering school, where we have roughly 600 desktop computers, okay, which are small workstation, okay, so Dell workstations. And we wanted to compare that first setup, that first scenario, with something that is more like a thin client and server approach, but where the thin client has even been replaced by something smaller in mass and in shape, which are single board computers. So in our study, for simplicity's sake, we consider a Raspberry Pi 4 SBC and some big workstation with dual processors, which have basically 100 cores each. Okay, so the idea was that we would replace those 600 computers by 600 single board computers and 6 servers, each server communicating or driving 100 units basically. And just for you to notice here, what we will compare, it's actually only the central units. So we exclude the external devices from our comparison, as they are both, I mean, they are used in both scenarios, okay? So we won't consider mouse, keyboards, or monitors, for example. Regarding the boundaries of our two systems, basically what we have, so if we try to express that in a life cycle style, assessment style. So as I said, we are using the IncoInvent 3.5 database for the background information. And regarding our models to model the functional unit that we discussed before, for example, for scenario 1, that's the kind of foreground model that we have. So that's one, I mean, that's one of the workstation where we will have what we call the components, basically the motherboard, the random access memories, the hard disk drive, the power supply unit, and so on. We will also include information related to the chassis, to the assembly of the part, to the packaging of the unit when it is sent to France, transport from the manufacturing and to Bordeaux. And we will also include end of life modeling or process. And regarding the use, basically it will only be the amount of electricity that we use during those 5 years of lifetime for those computers. And we have something similar with our scenario 2, with those 600 single board computers and the 6 servers. So it's very similar, at the exception that for the Raspberry Pi 4, as it's a very small board, I mean, we do not have something as complex as for either the desktop computer or the server. Basically, we only have one PCB with a few elementary electronic components soldered onto it. Okay, and for the server, it's kind of similar to the desktop computer, except that there are more individual components, or they are larger in size or in mass, as we'll see. Okay. So just a small point regarding the network requirements that are intrinsic to scenario 2. So the one with the single board computers and the servers. So if we have a look, basically for one server, we will have roughly 100 single board computers that are connected to it, which means that you absolutely need to have a network infrastructure to communicate onto those SBCs. The computations are not run on the single board computer, but on the server side. Okay. But the good news is that this kind of infrastructure is actually quite similar to the ones that we already have in our school anyway, because even with the desktop computers, we need to exchange data over the internet or over our local area network. So we already have that network infrastructure. And if we just try to give figures to those network links, if we assume a quite standard and even a bit outdated 1 gigabyte per second link, we will have roughly 10 megabits per second per SBC. So that's in theory. In practice, due to some network limitation or mechanism intrinsic to the network, you more have something between 5 to 8 megabits per second per SBC, but that's basically sufficient for most of the targeted digital software that we want to use. Okay. So if we dive into the lifecycle inventory, so first regarding the different phases of our lifecycle, what we will consider is that the production and the assembly of the products are performed in China. Okay. Then they are transported to France, where we use it, and that we will try as much as possible to consider the end of life in France. Okay. Which means that in IncoInvent, we tried as much as possible to use China location for the geography, and when not available, either rest of the world location or global if we had nothing better. And regarding the French parts, basically we try to use as much as possible the French geography in the IncoInvent locations. So for the components of the devices, regarding the desktop computer, we perform an inventory of the component from the Dell manual, which listed the main part, and also by, let's say, manual disassembly of one of such computers as those, we consider the computers that we have in our school. So we had access to some of those computers. For the key components, like the motherboard, the graphics processing units, or the random access memory, we even perform what we call a sub-component level modeling that I will present. I will present the methodology on the next slide. And for all the other main components, they are quite generics, like the hard disk drive, the DVD player, because we still have DVD players in our computers, or the power supply unit. We relied as much as possible on the generic processes directly available within the IncoInvent database. Regarding the server, basically we considered a similar approach for the key components, except that they are more numerous because the server will have significantly more RAM units. It also has something like 2 motherboards in that configuration, and the one that we have 2 GPUs instead of 1. And for the single board computers, we perform also a sub-component level modeling, but directly from the comprehensive list of components that is available on the internet. So for an older model, but it's quite similar in terms of layout. And the estimate that we got for the total mass was it was in agreement with the official documentation. So regarding the sub-component level modeling for the key components like the motherboard, the RAM, or the RAM units, or the GPUs. So first, those sub-components, so there are different categories for such sub-components. So either, let's say, integrated circuits, capacitors, inductor, or PCB, so printed circuit board, etc., etc. And we perform, we counted, when I say we, those are the 4 students that I mentioned before. Basically, during their semester project, they counted each type of those sub-categories. So the amount of items in all of these subcategories using .goose, which is a Python software that is dedicated to counting objects in a picture. So each dot here represents one of those passive elements, typically. So they counted more than 1,000 items on those kind of boards. And so at the end, you have the total number of those elements. And to evaluate the impact, you need either to have the mass of those components, for example, for the passive, okay? Or for other components like the integrated circuits, usually you rather use the area of those circuits. And in our case, we perform educated guesses based on the model of the processors and where we had access to pictures of the dies to estimate the actual area of IC within the package. So another important part of the system that we consider is the chassis of the devices. So basically the enclosure. So overall, the methodology that we use relied a lot on educated guesses. When possible, we try to average, to sample a few commercially available products in a similar category and to average, for example, the weight or the amount of plastic in those commercial products. And we had also we also performed some simplifications, like for fans, we only considered the plastic of those devices as it's the main material by far. So we did not account for the small pieces of PCBs or the small motors in those kind of systems, for example. So regarding the desktop computer, so here you have a picture of a similar, a computer similar to the one that we consider. Basically, that's a box of 5 kilograms of steel with a bit of plastics everywhere. It has a CPU cooling system, so that's not that one. It's it's here for illustration purposes. But basically, you have a system where you have copper heat pipes here that go to an aluminum heatsink, and you have a fan for extra ventilation. For convection. So we modeled those kind of system as it's a significant part of the metal. It's also a significant mass of metal, and we included in the chassis subsystem for simplicity's sake things like the power cable or the Ethernet cable as well. So for the server, we use a similar approach, except that you have significantly more material. Look, 5 kilograms for the desktop computer. On the server enclosure, it's more about 13 kilograms of steel. It also has a much larger CPU cooling systems and also more fans, but basically that's the same kind of system. And for single board computers, it's a bit different because for the enclosure, we considered using a custom enclosure in ABS, so a plastic that has good manufacturability and durability, and it avoids using aluminum that also have a significant impact, environmental impact. Based on our estimation, we would need typically about 50 grams of ABS per single board computer. And we considered that those would be 3D printed in a third-party 3D printing house in China, because otherwise it would take a very long time to print 600 enclosures in one or two 3D printers in the school. So regarding other parts of the inventory, like assembly, packaging, transport, and end of life, basically, as I said, assembly, we considered that it occurs in China. We used generic processes from EcoInvent when possible. For the packaging, we performed a rough estimation of the total amount of, the total amount of materials that would be needed to send the systems. So basically, we have card boxes and also from polypropylene. Typically, that's the kind of material that you find in those packagings. For the transport, so we considered 1,000 kilometers by truck in China to go, for example, from the factory plant to the port, where it's shipped in a cargo ship over roughly 15,000 kilometers, and we have about 1,000 kilometers by truck in France, for example, to come from Amsterdam to Bordeaux. That's roughly the distance. And regarding the end of life, as I said, we tried to keep it in France as much as possible in the geography of the EcoInvent processes. So another one of the remaining part in the inventory is the use of the devices over their whole lifetime. So here, just to be clear, the energy that those devices uses, it's electricity. And the amount that we consider, we relied on EU regulations for desktop computers or server computers. So they impose that kind of, equations where you have the energy consumed. So for a year, so that's the amount of hours in a year, and you consider fractions, different period of time with different usage. So for example, software off, a another period where the system is sleeping, and the period where you actually use the system. So they call it idle because they consider light bureaucratic usage typically. But in our context, it might, I mean, it's an open question if that's really representative of the actual use of our machines. And when you have also, I mean, you need those three types of powers. So that's what's given here in that table, where you have the three different phases for the scenario 1 and for the scenario 2. And the important information here is that when you account for the whole system over the 5 years, what you have is that from the scenario 1 to scenario 2, you have something like a 6-fold reduction in terms of electricity usage. Okay, so you go from 300,000 kilowatt per hour to roughly 50 kilowatt per hour. So just to be clear, so far we have kind of I mean, we have a lot of different building blocks, and it's an open question to, I mean, if we did significant mistakes when performing those that kind of inventory. So that's why we also try to perform sensitivity analysis. So for example, that's our that's our current scenario, where we have 600 single board computers and 6 servers over the 5 years. But we also consider some kind of a worst case scenario too, with single board computers that have a half lifetime, for example, because it's not very clear if they could run in those kind of contexts over 5 years. And we also consider that in a real world case, we would need spare for the servers in order to be able to quickly replace them in case you have a failure, because when you have one server that is down, it's about 100 computers that cannot be used for teaching activities. Okay. And another kind of sensitivity analysis that we perform is to consider different electricity mix from different locations. So basically French, European, or Pole electricity mix with different carbon intensity. So when you put everything together, you are able to perform the life cycle impact assessment. So first, for example, regarding the scenario 1, so the one with the desktop computer, that's the kind of result that we have, where each bar here is one of the impact category from the recipe assessment method, and the colors are for the different elements of the system boundary. So basically in orange, that's the electricity use, and in blue, that's the component impact. And first, what might not be a surprise is that the component impact, I mean, they account for more than 50% of the impact in 15 of those categories, okay? The only two that are not mainly driven by the component manufacturing are the ionizing radiation category and the water consumption category. And that comes mostly from the fact that in France, the electricity is produced from nuclear energy, which produce ionizing radiations and evaporate quite a lot of water, which is why this category is kind of high here. And if we dive in the global warming impact for one single of those computers, I know that some of you are quite familiar with that figure. Basically, so what we have here is one desktop computer over its whole life cycle. And in blue, you have the impact of the component. Okay, so that's the main impact by far. And one of the main sub-level, one of the components that account for roughly half of the impact is the motherboard. And within that category, what's really impacts are the integrated circuits. And by far, the most area in that category comes from the main processor, okay? So on those topics, I invite you to rewatch the previous ESOS seminars on those topics. And we also, based on those results, we might also want to investigate further the PCB impact for later studies, for example. So if now we have a look at the second scenario, what we can see is that in average, the single board computers, which are the darker areas, account for roughly 60% of the impact, okay, versus 40% for the servers. So we have a quite balanced situation, even though there are far more numerous single board computers. And something that is interesting here is that both scenarios, in terms of impacts, as they are actually quite similar, as you can see with that animation, where I go back to the first figure, we have roughly the same distribution regarding the component impact versus the use impact. But if now you compare them, if you perform a relative comparison of those two scenarios, what you have is that in orange, you have the scenario 1, and in green, you have the scenario 2, and you can see, for example, if we have a look at the global warming impact, that we reduce the impact of our functional unit from almost 40 tons of equivalent CO2 to 3.2 tons per year, okay? And overall, in all categories, we have roughly 85% to 90% of reduction of impacts. So in a nutshell, the scenario 2 is much more eco-efficient than scenario 1, both in the manufacturing-driven impact categories or the use-driven impact categories. If we have a deeper look in some of those impacts, for example, regarding the metal requirements. So here you have the metal requirements of scenario 1 versus the same for scenario 2. And again, you have something like a 90% reduction. And an interesting point here is that iron, which is used in steel, is the main metal used in both scenarios. But when it comes to mineral resource scarcity, on the right, again, scenario 1, scenario 2, what you see is that it's actually gold that is the most contributing metal to mineral resource scarcity. And so, for example, gold is used typically for electroplating in the PCBs. Okay. So that's not the same conclusion here. If we have a look at the global warming impact for each kind of devices, so the single board computer, the server, or the desktop computer, it's an opportunity, for example, to compare our study with the fact sheet from Dell, where basically we have a significantly different use phase or use impact, and it comes from the fact that Dell consider a different electricity mix. Okay, but when it comes to the manufacturing-driven impact categories, our results are quite similar to what Dell's announced. So we were quite happy with those results when we got them. Okay, and if now we look at the sensitivity analysis that we performed just to be sure that our results stands even if we had made significant mistake in the modeling. So what you have here, that's for the 3 different electricity mixes. So from the least carbon intensive to the most carbon intensive from left to right. And the different bars are for scenario 1 the ideal scenario 2 and the scenario 2 in its worst case scenario with extra single board computers and spare servers. And the main message here is that the orange part, which account for the use, it's heavily dependent on the intensity of the electricity mix. Okay. And in all the cases, even in the worst case scenario, scenario 2 is still, still provides a significant reductions in terms of global warming impact. Okay. Yeah, so that's what's written here. And so if we discuss a bit, so what's in the literature, I will try to speed up a bit, is that, so we have just seen the comparison with the DELT fact sheet, but one of the discussions that we could have is that the desktop computers that we consider are actually small workstation. We could have consider smaller desktop computer, which typically would have provided something like 10 to 15% less global warming impact compared to the ones that we used. And in the literature, you can find studies with, for example, all-in-one computers or a true thin client and server approach, which already reported significant reduction in terms of global warming impact. But when you compare to the solutions that I just presented, this work still suggests that single board computer could help to go even lower or higher in terms of reduction. But again, I am pretty sure that you are all aware of that. Those are to take with a pinch of salt because there are often caveats when comparing different, LCS from different origins or different methodologies. Okay. And something that we were asked by the reviewer to perform actually when we submitted the manuscript was to include a scenario where we consider that the student would be using not desktop computers, but a laptop that we would provide to them. So that's the scenario 3 here, where each one of our 1,200 students has a middle range laptop. And to have consistent comparisons, we then had to include the impact of the monitors and the mouse and the keyboards in the two previous scenario 1 and scenario 2. So those are the orange areas here. So first, we can see that the monitors account for a very significant they have a very significant global warming impact. So you might not want to replace them very often as well. And regarding the laptop-based scenario, it appears to be something like an in-between solution. But there are still a lot of open questions, like what is the usage pattern out of school by the student? What is the actual lifetime of laptop? Would it be 5 years in average? Or, for example, would they still purchase a personal laptop if we provided them with one? So to be fair, we would need a full LCA here for consistency. And something that might interest you is regarding the data that we used. They have some limitation. So as I said, we use the 3.5 version of EcoInvent for modeling the electronic components. And those data are mostly coming from the 2000s, okay? So they are not very up to date. I read yesterday that there might be some improvement on those topics regarding a more up-to-date version of the EcoInvent database. So it might be worth to update our own. And you have some databases that have more up-to-date electronic datasets, but they are not very compatible with the approach used in EcoInvent, for example. Regarding electricity, we could, for example, try to account for the extra air conditioning needed for the servers, even though we already have an air-conditioned server room in our case. And something that it's still quite unclear is the accuracy of the end-of-life processes in the IncoInvent database regarding the French situation. I mean, the situation in France of waste electrical and electronic equipment. Yeah. So just to conclude, we have shown, we have seen that using single-board computers and server might provide several benefits when it comes to the reduction of environmental impact compared to a solution with desktop computers. From experience, that's some kind of return of experience. It's a nice example to introduce life cycle assessment to engineering students, because that was the whole purpose of that study in the first place. And on a more practical manner, so from our studies, at least for our functional unit, manufacturing account for the vast majority of impacts, whatever the scenarios that you consider. And regarding the use phase, we have seen in our sensitivity analysis that it's heavily dependent on the carbon intensity of your electricity mix. Okay. But then the scenario 2, so the one with single-board computers, still provides significant reductions in terms of environmental impact. And in terms of perspectives, and that will be my last slide, we could argue about the cost of the scenario 2 option based on retail price. Basically, it should be significantly cheaper. But if Dell makes you a huge discount on the desktop computer, you might still need to have an extra analysis here. We could argue, we could investigate if it would be possible to use other types of single board computers, more open, like RISC-V based architectures, where the open specification might help to provide longer support or to be more versatile in the use of those kind of single board computers, hence longer lifetime, etc., etc. A true question on our side is, what about the quality of service in a more centralized approach? But to investigate that, we might need to set up a real-world experiment, for example, a few rooms. And my main message here, but I'm pretty sure that you are all convinced, is that to go further in those kind of analysis, we need for finer grain and more up-to-date data set when it comes to the environmental impact of electronics, because that was one of the limiting factors in our study. Thank you very much for your attention, and I will be glad to have questions if you have some, to answer questions.
Thank you, Adrien, for your presentation. I have one question to open the question. You use OpenLCA for students for presentation. Do you use another modeling tool for research works? For example, Brightway.
Yeah, so that's true that I did not explain that, but for example, among all those people, there is only one single person that actually do life cycle assessment as a research activity. That's Philippe Loubet. And basically, all of us only use OpenLCA. I know that Philippe also used Brightwave in some of his research activities. It's kind of an hybrid. He used both of them depending on the top. For the teaching purposes, it was simpler for us to use something with a graphical interface, and it was some Java-based software that helped deploying it on our own IT infrastructure, basically.
Okay, thank you. Does anyone have a question?
Yeah, I've got a question. Did you start to provide the student with the Raspberry Pi, or do you continue with the desktop computer?
So do we provide the list of,
Yes, do you apply the scenario too with your students?
Yeah, so that was actually one of the plans that we have when we wrote the paper, and the direction of the school was kind of aligned with that idea. Unfortunately, Ukraine happened, and we had some extra expenses. So for the moment, it's kind of on the back burner to buy such a server and to try to set up one of those rooms. But with my colleagues, that kind of still, I mean, that's still an option on the table to further investigate the questions that are raised in the end. Because, for example, the quality of service is a true question.
But was it well received by the IT team and by the direction of the school?
I mean, that's one of the issue. I mean, the open question again, because it's kind of significantly different from what they are used to manage, and those are platforms they are not really used to. But I mean, based on the results that we got, at some point we will have to reduce our school environmental impact, and that's a very, I mean, as I said, the IT infrastructure is one of the main contributor to our digital-oriented school. So that's an easy lever on that side.
That's another question. How did you take into account the storage? Because you speak about the computing, but the storage, because there is no storage on the Raspberry Pis or on the storage.
Yeah, so it would be typically on the server side, but again, that's kind of already what we have currently in our desktop-based system. So on the desktop, you have the OS and the software that are deployed and installed, but the student storage, that's a network storage. So it would not change our current setup. Only we would need some extra space to install all the softwares on the server side. But I mean, if you replaced 100 replicated installations with a single installation in a single install on the software side, we could even reduce the overall amount of storage that we need.
So there is a question about the quality of service here.
Yeah.
So maybe we need a upgrade on the Raspberry Pi.
There is a question from Muriel, so I'll ask for you. Is there a risk for rebound effect of adding Raspberry Pi SBCs, but at the same time keeping many PCs to keep the quality of service, and then maybe it would make sense also to make an LCA of a mix of both systems?
Yeah, so to answer the first question, that's always a potential issue, the rebound effect. But in the current case, I guess that we're in one of the few situations where it would be manageable, in the sense that if we were going to, I mean, if we switch to Raspberry Pi for the thin clients, basically we would not keep the desktop computers, because we don't have an infinite amount of space to double everything just in case. So it would be a hard transition, basically. I mean, there would be no spare desktop computer, at least in the rooms that we would switch to Raspberry Pi. So I guess that we would be safe regarding the rebound effect here. We which would be nice to evaluate in practice. And to answer the second question, so could we imagine a hybrid scenario? That's a very good question, and it might be the actual final solution that we would go for, because for some of the applications, a server-based approach might not be the best option if you have systems where you need a very high bandwidth, for example, or you need specific installs that do not really translate to a more centralized approach. We might want to keep a few lab workrooms with the old way, but the vast majority of our teaching rooms will be replaced with Raspberry Pi. That would be the idea. And based on the results that we got, we would still have a very significant reduction of the impact, because I mean it's a 10-fold reduction when you switch to the Raspberry Pi based solution.
Okay, thanks.
I have a question. Would the replacement be done in one go, or time at a time? Because well, you're in a situation where you have desktops right now, and you will replace them with Raspberry Pi. So what happens with those computers?
So now so the computers that we have, so in the studies that are presented, they would be handled, processed with recycling and so on in theory. So in practice here, what we would have, if we had to do it in our school, those computers would be offered to have a second life in either interested associations or other branch of the public service. So you have some system nowadays to perform that. And normally, if I'm correct, we do not replace our whole infrastructure at once. You have some, there are some kind of ladder. So we would replace a few rooms by a few rooms. All our PCs do not reach their end of life at the same time. Otherwise, it would be very hard to manage by the IT support guys, I guess. So yeah, it would be a gradual change, and the still functional computers that we will be replacing for administrative sake would be truly recycled, meaning that as much as possible they would be reused as it, rather than deassembled. Hopefully that answers the question.
I have a follow-up question. They would be replaced when they're they would be used the same amount of time, whether you would replace them with the Raspberry Pi or a computer. Like if you were to continue the scenario one, would they leave as much time as with scenario two? Because then, like in scenario two, you should account for the replacement, the early replacement of those computers.
So the scenarios that we consider were, they are permanent state scenarios, permanent regime scenarios. Of course, the transition period is an open question. If we were going to switch to Raspberry Pi system like in the scenario 2, it would be a gradual replacement, meaning that as soon as some of our workstation reach their end of life, and that's the administrative end of life, basically, every 5 years you need to replace them for accountability, for accounting reasons. So when they do so, we would replace them with Raspberry Pi. And nowadays, on top of that, those expired machines, they are offered to third parties, which might be other branch of the public service that would be okay with using PCs that have reached their end of life from an administrative point of view, or associations. So it would be kind of smooth in terms of transition. I mean, we would not replace them with scenario one approach with new computers.
Okay, I have a question regarding the teaching part.
Yeah.
Can you say a few words about who were the students, how many, how long was the course?
Yeah,
how many
okay.
lectures?
Yeah. So as I said, that work, I mean, we did not do research work to build a lab work with the students. It was actually the reversed. I mean, basically, we build a lab work on that life cycle assessment, and it ended up in being suitable for academic submission. And so the lab work that we have, it's within a 12-hour long period where we have 3 different lab works, and 2 of those lab works, so roughly 8 hours, are dedicated to life cycle assessment with OpenLCA and IncoInvent. And the main lab work is about the work that we presented here. Basically, the students are provided with the processes that we modeled in IncoInvent. They have to adjust some of the quantities to better represent the infrastructure that we have in school, and they perform some of the studies that, I mean, some of the calculations that we presented here. One of the minor changes in comparison to what I presented you is that for the use phase, we have another use pattern scenario that was more based on our educated guesses. And it's still an open question. We are trying to perform some power monitoring on those computers to have a better idea of what's the actual use pattern in our in the context of our engineering school. But anyway, as based on the French electricity mix, the use phase is not very the main driving factor. I mean, we are kind of, I mean, it won't change much the final conclusions. But yeah, basically the work here is used to present OpenLCA to the students and give them a real world use case. And why we chose the IT infrastructure or the computers that they use is that those teachings, they are for all the students in the engineering school, meaning that whatever their department is, they will perform that analysis. So we needed a topic that might interest all of those students. So the one in electronics major, but also the one in informatics major, or even mechanics. So they all use the computers. So that was the main reason why we chose that in the first place.
Thank you. Is there online questions? No. We could end the seminar. Thank you, Adrien.
Thank you.
For your time and your presentation.
Thank you.